Right now, as you watch this, something unprecedented is happening in our solar system. For months, astronomers have been tracking the interstellar visitor 3I/ATLAS as it journeys toward our Sun, carrying with it chemical signatures from another star system, another era of cosmic evolution. But what they've discovered in recent weeks has fundamentally challenged everything we thought we knew about solar physics. Our Sun is acting strange, and the timing couldn't be more disturbing. This isn't just another space documentary. This is the story of how a wanderer from the depths of interstellar space might be awakening forces in our own star that we never knew existed. Forces that could reshape our understanding of the universe itself, or potentially threaten the technological civilization we've built here on Earth. The story begins on a routine Tuesday morning at NASA's Solar Dynamics Observatory. Dr. Elena Vasquez, a solar physicist with 15 years of experience monitoring our star's behavior, was conducting her standard review of overnight coronal mass ejection data when she noticed something that, by all rights, shouldn't exist. "I've seen thousands of solar flare sequences," Dr. Vasquez later told her colleagues at an emergency meeting. "Random events following the chaotic patterns we've come to expect from magnetic field interactions in the solar corona. But this was different. This had structure. This had timing. This looked almost like the Sun was responding to something." The numbers were staggering and deeply unsettling. Solar flares occurring at rates 300% above baseline normal activity. Magnetic field fluctuations that defied every predictive model her team had developed over decades of solar research. And perhaps most disturbing of all, the timing of these events seemed to correlate precisely with observational reports from the teams tracking 3I/ATLAS. Every time the interstellar comet shifted trajectory, increased its outgassing rate, or displayed changes in its coma structure, within hours the Sun would respond with increased magnetic activity. Solar flares would erupt from active regions that had shown no previous signs of instability. Coronal mass ejections would burst forth from the solar surface, sending billions of tons of charged particles racing across the solar system at millions of miles per hour. At first, the correlation seemed like it had to be coincidence. The Sun is a complex, chaotic system where magnetic field lines twist and reconnect in patterns that can appear random, even to trained observers. Solar activity follows its own internal rhythms, driven by the 11-year solar cycle and the complex dynamics of plasma physics operating at temperatures exceeding 1,000,000 degrees Celsius. But as the weeks passed and 3I/ATLAS continued its inward journey, the patterns became impossible to ignore. Dr. Vasquez began collaborating with Dr. Marcus Chen at the Harvard-Smithsonian Center for Astrophysics, who had been leading one of the teams studying the interstellar visitor's unusual composition and behavior. 3I/ATLAS carries chemistry unlike anything ever observed in our solar system. Spectroscopic analysis revealed a coma dominated by carbon dioxide to an unprecedented degree, with CO2 to water ratios that challenged conventional models of comet formation. The object appeared to have formed in conditions so different from our local cosmic neighborhood that it might as well have come from an alien world, which in many ways it had. But the chemical anomalies didn't stop there. The comet's spectrum showed prominent emission lines from exotic metal compounds, including unusual concentrations of rare earth elements and isotopic ratios that spoke of formation around a star with dramatically different nuclear processes than our own Sun. Most intriguingly, the object displayed strong signatures of complex organic molecules, some of which appeared to be entirely novel compounds not found in any terrestrial or solar system database. Dr. Chen's initial hypothesis was that these exotic chemicals, when heated by solar radiation as 3I/ATLAS approached perihelion, might be creating electromagnetic effects that somehow propagated across the 150 million kilometers separating the comet from our star. The idea seemed preposterous on its face. How could a small comet, even one with unusual chemistry, influence the behavior of an object containing 99.86% of all the mass in our solar system? Yet the correlations continued to strengthen. When 3I/ATLAS underwent what appeared to be internal structural changes, evidenced by sudden brightening events, and alterations in its tail structure, these episodes were followed within 6 to 12 hours by corresponding increases in solar activity. The timing was too precise, too consistent, to dismiss as mere coincidence. The implications of these observations sent ripples of excitement and concern throughout the global community of solar physicists and space weather specialists. If confirmed, the correlations would suggest that our understanding of stellar behavior was fundamentally incomplete. More immediately, they raised serious questions about what might happen as 3I/ATLAS approached its closest point to the Sun. Dr. James Rodriguez, director of the Space Weather Prediction Center at NOAA, found himself in the uncomfortable position of trying to prepare for scenarios that had no precedent in the historical record. "We're dealing with completely uncharted territory," he explained to a hastily convened interagency meeting. "Our models for predicting space weather are based on decades of observational data, showing how solar activity affects Earth's magnetosphere and technology infrastructure. But we've never had to factor in the influence of interstellar visitors with exotic chemistry." The technological implications were sobering. Each solar outburst potentially triggered by 3I/ATLAS's approach threatened critical infrastructure systems that modern civilization depends upon. Satellite networks experienced intermittent communication blackouts as high-energy particles bombarded their sensitive electronics. GPS systems began providing coordinates that were hundreds of miles off their actual positions, creating navigation chaos for everything from commercial aviation to precision agriculture. Power grids across multiple continents reported unusual fluctuations as geomagnetic storms, induced by the enhanced solar activity, created electrical currents in transmission lines. In some cases, these induced currents were strong enough to trigger protective shutdowns of major transformers, leaving hundreds of thousands of people without electricity for hours at a time. Perhaps most dramatically, auroral displays began appearing at latitudes where they had never been observed in recorded history. The northern lights, typically confined to regions within 20 degrees of the magnetic poles, were photographed as far south as Mexico and North Africa. The southern lights appeared over populated areas of Australia and Chile, creating spectacular light shows, but also serving as visible evidence of the unprecedented disturbance in Earth's magnetic field. Airlines found themselves forced to reroute flights away from polar regions, where radiation exposure from solar particle events exceeded safe limits for both passengers and crew. The International Space Station implemented emergency protocols, with astronauts taking shelter in heavily shielded areas during the most intense solar storm periods. Several unmanned spacecraft reported systems failures as their electronics were overwhelmed by the flood of high-energy particles from our increasingly active sun. The financial implications of the crisis began to manifest across global markets. Stock exchanges in Tokyo, London, and New York saw significant volatility as investors struggled to price the risk of widespread infrastructure failures. Insurance companies found themselves trying to calculate potential claims from what could only be described as interstellar weather events. The Lloyd's of London insurance market activated catastrophe protocols, typically reserved for major natural disasters. Technology companies with satellite-dependent operations saw their stock prices fluctuate wildly as each solar outburst threatened their orbital assets. GPS-dependent services from ride-sharing apps to precision farming operations faced the prospect of extended outages. The emerging autonomous vehicle industry found itself confronting a scenario their engineers had never considered. What happens when the satellites that guide self-driving cars are rendered unreliable by interstellar chemistry? As 3I/ATLAS continued its approach toward perihelion, teams of scientists around the world worked frantically to understand the mechanism behind the apparent solar-comet connection. The physics seemed to defy conventional understanding. Electromagnetic effects fall off rapidly, with distance according to well-established inverse square laws. For a small comet to influence solar activity across astronomical distances would require energy coupling mechanisms that current science couldn't explain. Dr. Sarah Blackwood at MIT's Kavli Institute for Astrophysics and Space Research proposed one of the most intriguing theoretical frameworks. Her team suggested that 3I/ATLAS might be carrying exotic matter formed in the intense magnetic fields around its parent star, matter with properties that allowed it to interact with solar plasma through previously unknown electromagnetic resonances. Think of it like a tuning fork, Dr. Blackwood explained to her colleagues during a hastily convened international video conference. When 3I/ATLAS releases its exotic gases under solar heating, it might be creating electromagnetic signatures that resonate with specific frequency bands in the sun's magnetic field structure. These resonances could then amplify small disturbances into much larger instabilities. The tuning fork analogy provided a compelling framework for understanding how a relatively small object could trigger disproportionately large responses in our star. Just as a small vibration at the right frequency can shatter a wine glass, perhaps the exotic chemistry of 3I/ATLAS was creating electromagnetic vibrations that could destabilize much larger structures in the solar corona. Computer simulations based on Dr. Blackwood's resonance theory began to reproduce some of the observed correlations between comet behavior and solar activity. The models suggested that as 3I/ATLAS approached closer to the Sun, the electromagnetic coupling between the two objects would strengthen exponentially. If the theory proved correct, the period around perihelion could witness solar activity unlike anything in recorded human history. Meanwhile, space agencies around the world began implementing emergency protocols designed to protect critical infrastructure from potentially catastrophic space weather events. Satellite operators uploaded new software designed to place spacecraft into protective modes at the first sign of increased solar activity. Power grid operators installed additional surge protection equipment and developed rapid response procedures for disconnecting vulnerable transformers from the electrical network. The European Space Agency activated its Space Situational Awareness Programme to its highest alert level, coordinating with ground-based observatories and space-based assets to maintain continuous monitoring of both 3I/ATLAS and solar activity. NASA's Space Weather Analysis Office began issuing daily bulletins to government agencies and critical infrastructure operators, trying to prepare them for scenarios that had no historical precedent. Amateur radio operators around the world reported increasingly unusual propagation conditions as Earth's ionosphere responded to the enhanced solar radiation. Radio frequencies that normally provided reliable long-distance communication became erratic or unusable entirely. Emergency services dependent on radio communications began implementing backup procedures and alternative communication networks. The phenomenon was having unexpected effects on Earth's climate systems as well. The enhanced solar activity was driving increased heating of the upper atmosphere, causing subtle but measurable changes in atmospheric density at satellite altitudes. This increased drag was accelerating the orbital decay of some spacecraft and causing others to require more frequent orbital adjustments to maintain their positions. Meteorologists noted unusual patterns in the jet stream and upper atmospheric circulation that seemed to correlate with periods of enhanced solar activity. While the effects were subtle, They suggested that the electromagnetic disturbances triggered by 3I/ATLAS might be influencing Earth's weather patterns in ways that climate models had never anticipated. Public reaction to the emerging crisis varied dramatically across different populations and cultural contexts. In some regions, the unusual auroral displays and reports of technological disruptions triggered fears of apocalyptic scenarios. Social media platforms struggled to contain the spread of conspiracy theories, suggesting that 3I/ATLAS was actually an alien spacecraft deliberately interfering with Earth's technology. Religious communities found themselves grappling with theological implications of a visitor from another star system apparently influencing the behavior of our sun. Some interpreted the events as signs of divine intervention, while others saw them as evidence of cosmic forces beyond human understanding. The Vatican's Pontifical Academy of Sciences convened an emergency session to address questions from Catholic communities worldwide about the theological significance of interstellar visitors affecting solar behavior. Scientific institutions worked overtime to provide accurate information and counter misinformation, but the unprecedented nature of the situation made it difficult to provide definitive answers to public concerns. Dr. Neil deGrasse Tyson, director of the Hayden Planetarium, found himself making daily appearances on news programs to explain the science behind the crisis and reassure the public that while the effects were unprecedented, they didn't represent an existential threat to human civilization. Amateur astronomers around the world became citizen scientists, documenting the unusual solar activity and contributing observations to international databases. Photography enthusiasts captured stunning images of auroras at previously unimaginable latitudes, creating a visual record of one of the most extraordinary space weather events in human history. The International Astronomical Union established a special committee to coordinate amateur observations and ensure that valuable data wasn't lost in the flood of reports from non-professional observers. Educational institutions seized the opportunity to engage students with real-time scientific discovery. Universities around the world established 3I/ATLAS Watch programs, where students could contribute to the research effort by analysing data and making observations. The crisis, despite its challenges, was inspiring a new generation of young people to pursue careers in astronomy and space physics. As 3I/ATLAS approached within 1 astronomical unit of the Sun, roughly the distance between Earth and our star, the correlations between comet activity and solar behavior became even more pronounced. Each outgassing event from the interstellar visitor was now followed within hours by corresponding solar flares, as if the Sun was directly responding to chemical signals from its exotic visitor. Dr. Vasquez and her team documented magnetic field changes in the solar corona that appeared to propagate from regions closest to 3I/ATLAS's position. High-resolution magnetograms from the Solar Dynamics Observatory showed wave-like disturbances moving across the Sun's surface at speeds consistent with Alfvén wave propagation in solar plasma. These magnetohydrodynamic waves seem to originate from points where the line of sight from 3I/ATLAS intersected the solar surface. The implications were staggering. If 3I/ATLAS was indeed triggering these magnetic disturbances, it suggested that interstellar objects could influence stellar behavior through mechanisms that mainstream astrophysics had never considered. The discovery would require fundamental revisions to models of stellar dynamics and space weather prediction. International cooperation in monitoring the unprecedented events reached levels typically seen only during major crises. The European Space Agency, NASA, the Japanese Aerospace Exploration Agency, and space agencies from dozens of other nations shared data in real time through emergency coordination protocols. Ground-based observatories from Chile to Hawaii to Antarctica worked around the clock to track both 3I/ATLAS and the solar response to its presence. The Atacama Large Millimeter Array in Chile provided crucial radio observations of the comet's molecular emissions, revealing complex organic compounds that had never been detected in any solar system object. These exotic molecules appeared to form and dissociate in response to solar heating, creating a constantly changing chemical signature that somehow seemed to be communicating with our star. Radio telescopes around the world detected unusual emissions from the Sun during periods of enhanced activity, including coherent radio signals at frequencies that appeared to match resonances in 3I/ATLAS's molecular spectrum. The signals were too structured to be random plasma noise, yet too complex to decode with current understanding of solar radio physics. Dr. Chen's team at Harvard's Smithsonian made a breakthrough when they realized that the radio emissions from both 3I/ATLAS and the Sun showed similar harmonic structures. It was as if the two objects were resonating with each other across the vast distances of space, creating electromagnetic music that only their most sensitive instruments could detect. We're seeing something that challenges our fundamental understanding of how matter and energy interact on cosmic scales, Dr. Chen explained to an emergency session of the International Astronomical Union. The electromagnetic coupling between 3I/ATLAS and our Sun appears to be mediated by quantum mechanical processes that we're only beginning to understand. The quantum mechanical aspect of Dr. Chen's theory suggested that the exotic matter in 3I/ATLAS might exist in quantum states that allowed it to influence solar plasma through mechanisms similar to quantum entanglement. While the idea seemed to stretch the boundaries of known physics, it provided a framework for understanding how information could be transmitted instantaneously across astronomical distances. Physicists at CERN and other major research facilities began conducting experiments designed to test whether exotic matter created in stellar environments might indeed possess quantum properties that allowed for long-range electromagnetic coupling. The results were preliminary and controversial, but they suggested that the universe might be far more interconnected at the quantum level than anyone had previously imagined. As perihelion approached predicted to occur within days, the scientific community found itself holding its breath. Computer models suggested that the electromagnetic coupling between 3I/ATLAS and the Sun would reach maximum strength when the comet passed closest to our star. If Dr. Blackwood's resonance theory and Dr. Chen's quantum coupling hypothesis were both correct, this could trigger a solar outburst of unprecedented magnitude. Space weather prediction centers issued their strongest warnings in decades, advising satellite operators to power down non-essential systems and recommending that power grid operators implement preemptive load shedding in vulnerable regions. Airlines cancelled polar routes entirely, and several countries activated emergency protocols, typically reserved for nuclear incidents or natural disasters. The approaching perihelion passage also represented the moment when 3I/ATLAS would become essentially unobservable from Earth, hidden behind the Sun's overwhelming glare. This enforced observational blackout meant that the most critical phase of the entire encounter would unfold hidden from a direct human observation. Scientists would have to infer what was happening based on solar activity data and wait for the comet's re-emergence weeks later to assess whether it had survived its close encounter with our star. Dr. Rodriguez at the Space Weather Prediction Center found himself issuing daily briefings to government officials and infrastructure operators, trying to prepare them for scenarios that had no historical precedent. We're essentially flying blind into the most potentially dangerous space weather event in recorded history, he explained to a packed auditorium of emergency managers and technical specialists. The economic implications continued to ripple through global markets as businesses tried to assess their exposure to potential infrastructure failures. Manufacturing companies with precision electronic systems began implementing backup procedures that would allow them to continue operations even during extended power outages or satellite communication blackouts. Financial institutions stress-tested their networks against the possibility of communication failures that could disrupt trading and settlement systems. Even seemingly unrelated sectors found themselves vulnerable to the crisis. Modern agriculture relies heavily on GPS-guided equipment for precision farming techniques that optimize crop yields while minimizing environmental impact. Extended GPS outages could force farmers to revert to less efficient methods, potentially affecting food production on a global scale. The shipping industry, which depends on satellite navigation for efficient routing and collision avoidance, began developing contingency plans for operating under conditions where GPS systems might be unreliable for extended periods. Port authorities implemented enhanced traffic control procedures designed to safely manage vessel movements without satellite assistance. International security agencies quietly began monitoring for potential social unrest as public awareness of the crisis grew. History had shown that periods of widespread technological failure could trigger everything from conspiracy theories to actual civil disorder. Emergency response planners found themselves preparing for scenarios that seemed more like science fiction than real-world contingencies. The crisis was also highlighting the vulnerability of modern military systems to space weather effects. Advanced weapon systems, communication networks, and surveillance platforms all depended on satellite technology that could be disrupted by enhanced solar activity. Defense departments around the world began implementing protocols designed to maintain operational capability even during severe space weather events. Yet amid all the concern and preparation, there was also a sense of witnessing something genuinely historic. For the first time in human history, we were observing direct interaction between our solar system and a visitor from another star. Regardless of the immediate challenges it posed, 3I/ATLAS was providing unprecedented insights into the interconnected nature of cosmic phenomena. The chemical analysis of the comet's exotic composition was advancing our understanding of stellar nucleosynthesis and planetary formation in other stellar systems. Every spectrum obtained from 3I/ATLAS carried information about nuclear processes that had occurred around a different star, possibly billions of years ago and hundreds of light years away. The apparent electromagnetic coupling between the comet and our Sun, if confirmed, would represent a breakthrough in understanding how matter and energy interact across astronomical distances. The discovery could lead to new insights into everything from stellar evolution to the propagation of magnetic fields in interstellar space. Universities around the world began developing new courses and research programs focused on interstellar archaeology, the study of objects from other stellar systems and what they could tell us about cosmic evolution. The field was attracting some of the brightest young minds in physics and astronomy, drawn by the prospect of exploring genuinely unknown territory in our understanding of the universe. The crisis was also driving rapid innovation in space weather monitoring and prediction technologies. New instruments designed to detect the subtle electromagnetic signatures associated with interstellar visitors were being fast-tracked through development and deployment. The next time an object, like 3I/ATLAS, entered our solar system, humanity would be better prepared to study and understand its effects. As the hours counted down to perihelion passage, observatories around the world maintained continuous monitoring of solar activity while amateur astronomers photographed the last visible traces of 3I/ATLAS before it disappeared into the solar glare. The comet's tail had grown to impressive proportions, stretching across several degrees of sky and displaying the complex structure that had become its signature characteristic. Ground-based coronagraphs, designed to block the sun's overwhelming light, were positioned to catch any glimpse of 3I/ATLAS during its closest approach. Space-based solar observatories prepared to record whatever interaction might occur when exotic matter from another star system encountered the plasma environment of our Sun at point-blank range. The final 24 hours before perihelion brought a crescendo of activity that confirmed the worst fears and highest hopes of the scientific community. 3I/ATLAS brightened dramatically as solar heating drove volatile sublimation to peak levels. The comet's spectrum showed new emission lines appearing and disappearing as different chemical species reached their sublimation temperatures. And with each change in the comet's composition, corresponding changes rippled across the sun's magnetic field structure. Solar flares erupted with increasing frequency and intensity, creating a spectacular display of stellar fury that was visible in real time through specialized solar telescopes. Coronal mass ejections launched billions of tons of charged particles into space, creating shockwaves that would reach Earth within days. The sun's magnetic field showed distortions and instabilities that propagated across its entire visible surface, creating patterns that seemed to mirror the complex structure of 3I/ATLAS's tail. And then, just as predicted, 3I/ATLAS disappeared into the solar glare, hidden behind the overwhelming brightness of our star. The direct observations ended, but the solar response continued and intensified. For the next 72 hours, the sun displayed levels of activity that exceeded anything in the modern instrumental record. Astronauts aboard the International Space Station reported seeing continuous auroral activity through the station's small windows, with the lights extending far beyond the polar regions where they normally appeared. The space station's radiation monitoring systems recorded particle flux levels that required crew members to take shelter in the most heavily shielded sections of their orbital home. On Earth's surface, power grid operators worked around the clock to manage the effects of geomagnetic storms that induced powerful electrical currents in transmission lines. Several major metropolitan areas experienced rolling blackouts as protective systems triggered to prevent permanent damage to expensive transformers and other critical infrastructure. Communication satellites in geostationary orbit found themselves bathed in high-energy particles that caused temporary failures of sensitive electronic systems. Some spacecraft were placed into safe mode automatically by their onboard computers, while others required manual intervention by ground controllers to prevent permanent damage. The crisis reached its peak approximately 48 hours after 3I/ATLAS disappeared behind the sun. Magnetometers around the world recorded magnetic field fluctuations of unprecedented intensity, while ionospheric monitoring stations detected disturbances that propagated through Earth's upper atmosphere like waves on a pond. And then, almost as suddenly as it had begun, the activity started to subside. Solar flare rates decreased toward more normal levels. The magnetic field distortions in the sun's corona began to fade. Earth's magnetosphere gradually returned to its typical configuration as the stream of enhanced solar particles diminished. The immediate crisis was over, but the questions it raised would persist for years to come. Had humanity just witnessed the first confirmed example of interstellar matter directly influencing stellar behavior? Were the electromagnetic coupling effects real, or had the correlation been an extraordinary coincidence? And most importantly, what would happen when 3I/ATLAS re-emerged from behind the sun in several weeks? The scientific community began the painstaking process of analysing the massive amounts of data collected during the crisis. Terabytes of observations from space-based and ground-based instruments would require months or years to fully understand. But already, preliminary analysis was suggesting that the correlations between 3I/ATLAS and solar activity had been even stronger during perihelion than anyone had predicted. International committees were formed to coordinate the analysis effort and ensure that all relevant data was shared among researchers worldwide. The potential implications of the discoveries were too important to be limited by national boundaries or institutional rivalries. This was science on a truly global scale, addressing questions that affected all of humanity. Economic markets began to stabilize as the immediate technological threats subsided, but the longer-term implications of the crisis continued to influence everything from insurance rates to investment strategies. The demonstrated vulnerability of modern technological infrastructure to space weather effects prompted calls for increased investment in protective systems and backup technologies. The crisis had also revealed gaps in international cooperation that needed to be addressed before the next major space weather event. Communication protocols between space agencies had sometimes broken down during the most critical phases of the crisis. Data sharing agreements proved inadequate when time-critical decisions needed to be made. These lessons would inform preparations for future encounters with interstellar visitors. Educational institutions found themselves dealing with unprecedented interest in astronomy and space physics programs. Applications to graduate programs in these fields increased dramatically as young people were inspired by the real-time scientific discovery they had witnessed. The crisis had demonstrated that space science wasn't just an abstract academic pursuit. It had immediate relevance to the technological civilization that humanity depended upon. Religious and philosophical communities continued to grapple with the implications of confirmed interaction between our solar system and matter from other stellar systems. The universe had revealed itself to be more interconnected and dynamic than many had imagined, challenging some traditional views about Earth's special place in the cosmos while affirming others about the profound mystery of existence itself. As weeks passed and 3I/ATLAS remained hidden behind the Sun, computer models began predicting when and where the comet would re-emerge into visibility. The calculations suggested that it would first become observable by space-based coronagraphs in the pre-dawn sky, gradually becoming visible to ground-based telescopes as it moved away from the Sun's glare. The re-emergence would provide the first opportunity to assess whether 3I/ATLAS had survived its close encounter with our star intact, or whether thermal stresses had fragmented it into multiple pieces. Either outcome would provide valuable scientific data, but an intact comet would offer the best opportunity for continued study of its exotic chemistry and electromagnetic properties. Preparations began for what would likely be the most intensive observational campaign in astronomical history. Every major telescope on and off Earth would be trained on 3I/ATLAS when it became visible again. New instruments specifically designed to study interstellar visitors were being rushed to completion and deployed at strategic observatories around the world. The re-emergence would also provide the first test of whether the electromagnetic coupling effects continued after perihelion, or whether they had been destroyed by the intense heating and gravitational stresses of the Sun's close encounter. If the coupling persisted, it would provide continuing opportunities to study the phenomenon and perhaps understand its underlying physics. Amateur astronomers around the world were already planning their own observation campaigns, eager to contribute to the continued study of this remarkable visitor from another star. Photography equipment was being upgraded, and new observing sites selected to maximize the chances of capturing useful scientific data when 3I/ATLAS returned to visibility. The story of 3I/ATLAS was far from over. Whether it represented new physics, cosmic coincidence, or something even more extraordinary, This ancient wanderer from the depths of interstellar space had already transformed our understanding of how connected our solar system is to the broader galactic environment. Our sun had acted strange, and in doing so, it had revealed that the universe is far more dynamic and interconnected than we had ever imagined. The cosmos, it seemed, was full of surprises for those patient and clever enough to detect them, and humanity was finally advanced enough to not just witness these cosmic conversations, but perhaps even to begin understanding the language in which they were conducted. The crisis had also revealed fundamental questions about humanity's readiness for contact with truly alien phenomena. While 3I/ATLAS appeared to be a natural object rather than evidence of extraterrestrial intelligence, its exotic chemistry and unprecedented effects on our sun had challenged assumptions about what constituted normal cosmic behavior. If a simple comet from another star system could have such dramatic effects, what would happen if humanity encountered something genuinely artificial in origin? The search for extraterrestrial intelligence community found itself grappling with new questions about what forms alien contact might take. Traditional SETI programs had focused on radio signals and optical communications, but 3I/ATLAS had demonstrated that alien influence might manifest in far subtler ways, through chemistry, electromagnetic effects, or quantum mechanical processes that we were only beginning to understand. Dr. Jill Tarter, former director of the Center for SETI Research, noted that the crisis had highlighted gaps in humanity's preparedness for any form of cosmic contact, whether natural or artificial. "We've been looking for messages in radio telescopes," she observed, "but we might have missed entirely different forms of information encoded in the chemistry and physics of interstellar visitors." The philosophical implications extended beyond questions of alien contact to fundamental issues about the nature of consciousness and intelligence in the universe. If matter itself could carry information across interstellar distances, as suggested by the electromagnetic coupling between 3I/ATLAS and our Sun, then the boundary between living and non-living systems might be far more complex than previously imagined. Some researchers began exploring whether the exotic chemistry of 3I/ATLAS might represent a form of distributed intelligence, not conscious in any human sense, but capable of processing and transmitting information on cosmic scales. The idea remained highly speculative, but it suggested new frameworks for thinking about intelligence that transcended the biological systems familiar to Earth-based life. The crisis had also accelerated development of technologies that would be crucial for humanity's long-term survival in a dynamic galactic environment. Enhanced space weather monitoring systems, improved electromagnetic shielding for critical infrastructure, and more robust communication networks all emerged from the urgent need to protect civilization from cosmic threats. Research into exotic matter and electromagnetic field manipulation received unprecedented funding as governments and private institutions recognized the potential military and commercial applications of technologies that could harness or defend against the kinds of effects demonstrated by 3I/ATLAS. The boundary between basic science and practical technology was blurring as researchers raced to understand and potentially exploit the phenomena they had observed. International space law found itself confronting questions it had never needed to address. If interstellar visitors could influence solar activity and thereby affect all nations on Earth, who had authority to make decisions about how to respond? The crisis had been natural in origin, but future encounters might require active intervention or even attempts to alter the trajectory of incoming objects. The United Nations began developing new frameworks for international cooperation in responding to cosmic threats that transcended national boundaries. The existing Outer Space Treaty provided some guidance, but it had been written in an era when interstellar visitors were purely theoretical concerns rather than observed phenomena with measurable effects on human civilization. Legal scholars debated questions about property rights and jurisdiction over objects that originated from other stellar systems. If 3I/ATLAS contained valuable materials or information, who would have the right to claim them? The object's interstellar origin placed it outside any existing legal frameworks for resource exploitation or scientific study. Environmental scientists began considering the long-term implications of regular interactions with interstellar matter. While 3I/ATLAS appeared to pose no direct biological threat, future visitors might carry exotic chemistry or even microorganisms that could affect Earth's biosphere in unpredictable ways. Planetary protection protocols would need to be developed to address contamination risks from both directions. Preventing Earth-based organisms from contaminating interstellar visitors and protecting Earth from potentially harmful alien chemistry. The crisis had demonstrated that Earth's technological civilization existed within a much more dynamic and interconnected cosmic environment than previously understood. The implications extended far beyond academic astronomy to touch every aspect of human society, from the technology that powered modern life to the philosophical frameworks that shaped human understanding of our place in the universe. Educational systems around the world began incorporating lessons from the 3I/ATLAS crisis into curricula at all levels. Elementary school students learned about the solar system's connection to the broader galaxy through simplified versions of the electromagnetic coupling story. High school physics classes used the crisis as a case study in how scientific theories are tested and revised when confronted with new evidence. Universities established new interdisciplinary programs combining astronomy, physics, engineering, and social sciences to address the complex challenges revealed by the crisis. The need for scientists who could work across traditional disciplinary boundaries became apparent as the interconnected nature of cosmic phenomena demanded more holistic approaches to research and problem solving. Medical professionals began studying potential health effects of enhanced space weather exposure, particularly for frequent air travelers, astronauts, and people living at high altitudes where Earth's atmospheric shielding is less effective. While the immediate crisis had not produced measurable health impacts, longer-term exposure to elevated cosmic radiation could pose risks that needed to be understood and mitigated. The psychological effects of the crisis also required attention. Many people had experienced anxiety about the vulnerability of modern technology to cosmic forces beyond human control. Support groups formed to help individuals cope with feelings of cosmic insignificance or fears about future space weather events. Mental health professionals developed new therapeutic approaches for addressing cosmic anxiety, a condition that had barely existed before the 3I/ATLAS encounter. Religious communities found themselves engaged in deep theological discussions about the implications of confirmed cosmic interconnectedness. Some saw the events as evidence of divine design in the universe's structure, while others interpreted them as challenges to anthropocentric views of creation. New forms of cosmic theology emerged that attempted to integrate scientific discoveries about galactic-scale phenomena with traditional spiritual beliefs. The art and literature communities responded to the crisis with an explosion of creative works inspired by the demonstrated connection between Earth and the broader cosmos. Musicians composed symphonies that incorporated the radio frequencies detected from 3I/ATLAS. Visual artists created installations that attempted to represent the electromagnetic fields linking interstellar matter to stellar activity. Writers explored themes of cosmic connection and humanity's place in a universe far more dynamic than previously imagined. Science fiction writers found themselves confronting the reality that many of their speculative scenarios had been too conservative. The universe revealed by the 3I/ATLAS crisis was stranger and more interconnected than most fictional accounts had dared to imagine. New subgenres emerged that focused on realistic portrayals of cosmic interconnectedness and its implications for human civilization. The economic impacts of the crisis continued to ripple through global markets months after the immediate emergency had passed. Insurance companies restructured their risk models to account for space weather events that could affect multiple sectors simultaneously. New financial instruments emerged to help businesses hedge against cosmic weather risks, while entrepreneurs developed products and services designed to operate reliably even during severe space weather conditions. The renewable energy sector experienced unexpected growth as the crisis highlighted the vulnerability of centralized power grids to geomagnetic disturbances. Distributed energy systems and localized storage technologies became increasingly attractive as methods for maintaining electrical power during space weather events that could disrupt large-scale transmission networks. Space-based manufacturing and resource extraction industries began serious development as the crisis demonstrated both the risks and opportunities associated with cosmic phenomena. Companies started planning facilities that could operate beyond Earth's magnetosphere, either to avoid space weather effects entirely or to take advantage of the unique conditions created by enhanced solar activity. The computing industry accelerated development of radiation-hardened electronics and quantum computing systems that could potentially operate reliably even during severe space weather events. The demonstrated vulnerability of conventional electronics to cosmic radiation created new market opportunities for technologies that had previously been considered too expensive or exotic for widespread adoption. Agricultural scientists began investigating the potential effects of cosmic weather on food production systems. While the immediate crisis had not significantly affected crop yields, longer-term changes in upper atmospheric chemistry or space weather patterns could influence everything from soil chemistry to the behavior of migratory pollinators. Transportation industries implemented new protocols for operating during space weather events. Airlines developed more sophisticated models for route planning that considered cosmic radiation exposure and communication reliability. Shipping companies invested in backup navigation systems that could function independently of satellite networks during GPS outages. The crisis had also accelerated human expansion into space as governments and private companies recognized the need for backup systems and redundant infrastructure beyond Earth's atmosphere. Plans for lunar bases, Mars colonies, and orbital manufacturing facilities received increased funding as humanity began to see space development not as an optional adventure, but as a necessary hedge against cosmic risks. Space elevator and orbital tether projects gained new support as the crisis demonstrated the economic value of reliable, weather-independent access to space. The ability to maintain critical infrastructure beyond Earth's magnetosphere became a strategic priority for nations and corporations alike. The scientific instruments developed to study 3I/ATLAS found applications far beyond astronomy. Enhanced magnetometers designed to detect subtle electromagnetic coupling effects proved valuable for geological surveys and mineral exploration. Spectroscopic techniques refined for analyzing exotic interstellar chemistry enabled breakthroughs in materials science and pharmaceutical research. Quantum sensing technologies, developed to investigate possible quantum mechanical aspects of the solar comet coupling, found uses in medical imaging, precision manufacturing, and fundamental physics research. The interdisciplinary nature of the research effort had produced technological spillovers that benefited fields far removed from astronomy and space science. The crisis had also revealed the importance of international coordination in addressing global challenges. The successful sharing of data and resources during the emergency provided a model for cooperation on other issues that transcended national boundaries, from climate change to pandemic response to asteroid defense. New institutions emerged to facilitate ongoing international cooperation in space weather monitoring and response. The Global Space Weather Consortium brought together government agencies, research institutions, and private companies from around the world to maintain the enhanced monitoring capabilities developed during the crisis and prepare for future events. Amateur astronomy communities found themselves playing increasingly important roles in cosmic monitoring efforts. The distributed nature of volunteer observers around the world provided coverage that no single professional institution could match. New citizen science programs channeled amateur enthusiasm into systematic observation campaigns that contributed valuable data to research efforts. The open source movement expanded into space science as researchers recognized the value of collaborative approaches to analyzing the massive datasets generated by modern astronomical instruments. Software tools developed by volunteer programmers enabled scientists around the world to participate in analyzing 3I/ATLAS observations, regardless of their institutional affiliations or funding levels. Social media platforms developed new capabilities for coordinating scientific observations and sharing data in real time during cosmic events. The 3I/ATLAS crisis had demonstrated the value of rapid information sharing, but also the dangers of misinformation during periods of uncertainty and fear. As the weeks passed and the time approached for 3I/ATLAS to re-emerge from behind the sun, preparations intensified for what would likely be the most comprehensive astronomical observation campaign in human history. Every major telescope on and off Earth was being prepared to study the comet when it became visible again. New space-based observatories designed specifically for studying interstellar visitors were being fast-tracked through development and launch. The crisis had provided compelling justification for investments in specialized instruments that could detect and analyze future cosmic visitors before they had significant effects on solar activity. Ground-based telescope networks implemented new coordination protocols to ensure continuous monitoring of 3I/ATLAS from multiple locations around the world. The goal was to eliminate any gaps in observation coverage that might cause important phenomena to be missed. Amateur astronomers organized global observation campaigns with unprecedented levels of coordination and standardization. Online platforms enabled real-time sharing of observations and collaborative analysis of data from hundreds of independent observers. The re-emergence would provide the first opportunity to assess what had happened to 3I/ATLAS during its hidden passage behind the sun. Computer models suggested several possible outcomes ranging from complete survival to catastrophic fragmentation, each of which would provide different types of scientific information. If the comet had survived intact, continued monitoring of its electromagnetic coupling with the sun would provide opportunities to test and refine the theoretical frameworks developed during the crisis. If it had fragmented, the multiple pieces might reveal information about the object's internal structure and composition that would otherwise remain hidden. Regardless of 3I/ATLAS's condition, when it re-emerged, the crisis had already transformed humanity's understanding of our place in the cosmic environment. We had learned that our solar system was not an isolated island, but rather an active participant in galactic-scale processes that connected us to stellar systems across the galaxy. The electromagnetic coupling between 3I/ATLAS and our Sun, whether ultimately explained by new physics or extraordinary coincidence, had demonstrated that the universe operated according to principles and connections that we were only beginning to understand. Every interstellar visitor carried with it the potential to reveal new aspects of cosmic reality that could transform our understanding of how the universe worked. Our sun had acted strange, but in doing so, it had revealed that strangeness might be the normal state of a universe far more dynamic and interconnected than human science had previously imagined. We were not just observers of cosmic phenomena, but participants in cosmic conversations that had been ongoing for billions of years. The real adventure was just beginning. As 3I/ATLAS prepared to re-emerge into visibility, humanity stood ready to continue learning the language of the cosmos, and perhaps even to begin speaking it ourselves.